Hello. So now that we sort of have a geometric or visual sort of idea of what's involved with using derivatives, taking derivatives, sort of what they kind of are, now we get the fun of diving into the algebra. So remember, derivatives, right, are these sort of classic difference quotients that we've already done when we did the average rates of change. But we're throwing in this idea of using a limit so that we can shift it toward instantaneous rates of change. So in general, if we want we have some function f of x, and we want to know the derivative at a given x value, say b, then we want to determine, right, the instantaneous rate of change of f of x at b, which means that we want to solve that classic difference quotient, this limit as x goes to b of f of x minus f of b divided by x minus b. Okay. But it turns out that instead of sort of doing that directly every time, sometimes it's useful to use that form, but there's sort of a second way of doing this. So instead of thinking about it, right, as this second point sort of that we're after, we want to think of it as taking that second point, merging with the first point, and instead of tracking the points, we want to track the distance between those points. So instead of thinking of x going to b, for example, we want to think of the distance from b of x going to 0. And we want to give this distance a name, so we call this thing delta x. So to be clear, that is this delta is technically capital delta as a Greek letter, but it's this triangle looking thing here. So if you haven't seen that before, that's what that is. You will also sometimes see this as h, although in most of the literature, it's usually delta x. We're going to use that as our sort of go-to notation just so that you're sort of familiar with it. So looking then at our original difference quotient, this limit as x goes to b piece, right? This is thinking of x merging to b, and we're replacing it now with this idea of that distance from b going to 0. So instead, we're going to be looking at, right, instead of having x go to b, we're going to have the delta x, that distance, go to 0. And instead of having x here, we're going to look at b plus the distance away from b that x is. So this b plus delta x is what that x was, only now it's b plus the distance from b that x is, right? So instead of measuring x going to b, we're measuring that delta x going to 0, which means that we'll be at f of b when that delta x piece goes to 0, this first piece turns into f of b. And to note, right, we wrote this bottom, we can obviously sort of simplify this, we'll do that in a second, but that's what this bottom is I've converted, right, the x to b plus delta x in both cases, right? So simplifying then, we can get rid of that b minus b in the bottom, and we get down to just delta x in the bottom, and we have this f of b plus delta x minus f of b at the top as delta x goes to 0. So again, to be clear, this is exactly the same thing. It's not a different equation. It's the exact same equation. The difference is how we're looking at what's happening. So instead of having x going to b, we have that distance going to 0, and we replace x with b plus that distance, okay? So then how do we evaluate this? Well, obviously, we sort of need a specific function when we're going to go through this, but it's worth a note that really most of the effort in dealing with this difference quotient arises in trying to get rid of that delta x in the bottom, right? Because right off the bat, if we tried to do some sort of substitution, right, for delta x being 0, well, that's going to end up blowing this thing up, right? Because I have 0 in the bottom. But I also have 0 in the top, right? Because I'll end up with f of b minus f of b. So there's some sort of simplification that would need to happen. That's what most of the effort ends up being when you're trying to solve this. So as mentioned sort of when we talked about the intro, our goal is not necessarily to sort of solve this difference quotient every single time. That would be incredibly time consuming. Instead, we want to develop techniques that let us sort of tackle a function and sort of do things that will make it simpler so that we can quickly do these derivatives. In particular, we want to develop rules that tackle each of our core function types, so like polynomials, exponentials, logs, whatever. Then we also want to develop rules that allow us to handle combinations of functions, like if we have addition of pieces together, or subtraction, right? Like an f plus a g, or x squared plus x cubed, for example, that let us sort of take derivatives of these things separately, so that if we have big stuff, we can sort of chunk out sections and tackle smaller pieces at a time. And finally, we want to look at how we can handle composition of functions, which sort of, until you learn to see functions as compositions, it seems like that might be like a really niche or rare thing to run into, but they are everywhere. Just almost everything is a combination of functions in some way. So composition of functions in some way, also combinations. So these things will get used a lot once we develop them. Okay, so our goal sort of moving forward, right, is to sort of have these three pieces tackled, right? The core functions, combinations, and compositions, and use that to break everything apart into smaller pieces. So, on the one hand, this idea of derivatives is essentially the same as the instantaneous rate of change that we did when we were doing limits, but our goal here is to approach this sort of algebraic aspect in a different way. And in particular, we're trying to approach it in what we might consider an actual mathematical approach, which I realize, you have a background having learned math, but a lot of the times the actual mathematician approach is sort of overlooked. So this is one of the arguably first times this is going to come up for you. And the idea is that we try to solve a more general problem, right? We try to think about compositions of functions in general, combinations of functions in general, right? These different aspects, like a core function in general. How do you tackle that piece? And by solving this more general problem, it makes solving specific stuff way easier. So that's what we're going to be doing moving forward. Okay. So that is that.